Hi, I'm Dr. Alexander NGENZI from University of Rwanda College of Science and Technology, Department of Computer and Software Engineering. Domain to their discrete values. So and we have seen some of the examples and the steps for how you can go about it. So we are going to see some of the properties of Z transform. So we have seen Z transform, inverse Z transform, and their calculations using the various steps that we have seen. Now we are going to see the properties, we can call it Z transform properties. Z transform properties. So we begin with property number one of what we discussed even from the beginning. We say when we are looking for a region of convergence, we discuss some of the properties, but we are going to repeat them so that when we are calculating them, or if you are given some systems or signals, you can be able to see how it behaves. We said number one is going to be linearity. So we said, for example, in case of linearity, we say what is done on the left-hand side is going to be the same, but being converted in its correspondence. For example, if it is from discrete value to their corresponding frequency domain, it's going to be the same. Suppose if we have a signal, if we have, for example, if we have x1 of n signal transforming it using Z transform, then it's going to be their corresponding frequency domain, which is big X of 1 into Z in this case. And the region of convergence is going to be the other one in the circle, the unit circle, which is R. And this is going to be the region of convergence. This case is going to be a unit circle in the middle. So it's going to be R1, for example, in this case. So if you have x of 2, this is small x of n, then converting it into their corresponding x of 2 z, then it's going to be a region of convergence is going to be R2. That is linear. It's linearity. It's going to be what is done on the left is going to be the same as what is on the right hand side. So this is very important to note that the linearity of the system given, for example, any value. For example, if we say ax1, for example, of n plus. So this is going to be, for example, bx2 of n. To convert it into the Z transform, the Z transform is going to be their corresponding side. So it's going to be x of 1 of Z plus x of Z. And with the region of convergence is going to be the intersection of A and B, because you are trying to combine them. Then if you combine them, for example, in case of R1 and R2, it's going to be the intersection of these values, for example, where the value is going to be intersecting from. The region of convergence is going to be R1 intersection R2. So it's going to be so suppose if you have this value of the region of convergence at any given value of R, for example, here, and for example you have another convergence value for R2, then this value is going to be the region of convergence, and hence is going to be the intersection where they meet is going to be the value of region of convergence. That is property number 1, which respects linearity. So by linearity, we are trying to mean what is done on the left hand side is going to be the right hand side, but they are corresponding values. For example, if you are looking for the frequency values, that's what we are going to obtain. So that is the property number 1. Now we are going to discuss, we are going to see property number 2. Number 2 is going to be time shifting. Remember we said n-1, n-2, with the function is shifting from left, shifting from right. That is what we call the time shifting. So in this case, we are going to see how the information. So if you can remember we said x of n, small n. If you do z transform, it's going to be big X of z. And hence, if we have a value, for example, shifted from any value small x of n minus n0, for example, is going to be, when we are using the z transform on this side, is going to be big X of the value inside z. In this case, if we use z transform, remember, it's going to be exponential of the value. So it's going to be the exponential of value of, it's going to be z power n0. That is a shift theorem into the x. Okay, it's going to be z power negative 0 x, because it is our function of z. So this is what we call shift. So we have shifted to the right, for example, the value n0. So in this case, if the value was supposed to be n, then it is shifted right at n0, for example, at any value n is equal to 0. So in this case, for example, if you have to remember this. So this is the left hand side, and this is going to be your value of the region of convergence at that one. So the value in this case is going to, so the R is going to be R, region of convergence. Region of convergence is going to be R, of course. And in this case, n0 is an integer. For example, here you can put it 1 or 2, but it is given it is an integer value, meaning that at this real number is an integer value. If positive shift, and if the negative shift, then is going to be there to correspond. And this is a positive shift. But if it is a negative shift, then it will be n plus n0. So you are trying to equate the value from the left hand side. So people confuse by looking at the plus sign or negative sign, thinking that they are corresponding shift, but they are not. So it's like, for example, n is equal to n0. So if you equate this one, so this one you can see it's a positive value, and therefore it has shifted to the positive side, which is the right hand side. And remember, the values there, they are negative. So let us just take an example from the shift value for a z transform. Given a z, the discrete value like this one, which is in discrete value form is going to be shifted by 1, then it will be n minus 1 xz. So if we are using a shifting theorem, remember we are going to shift it by -1 in this case. So it's going to be, so the xz is going to be z power -1 into 1 over that value, which is a quarter, going to be 1 minus a quarter, which is this side, but is in terms of partial z, this side, from where region of convergence is going to converge from modulus z, which is bigger than a quarter in this side, because we are trying to calculate the z transform. So that is a very simple example. The reason being, so you can see here is going to be 1 over 1 minus z. Then when multiplying this one is going to be exponential, then nothing else is going to be. So here you can see there are two values here. So we are going to calculate at z equals to less than a quarter. So I hope you understand. This one is going to be determined in this case, and this one, when transforming it, is going to be this case. And if you calculate, you are going to get the modulus z, or this is the region of convergence. This is the region of convergence. This is very easy to know the shift time. And this one, if you can recall what we said from the previous examples and previous equations that relate to z transform and the inverse z transform. So all these values to be converted to their corresponding frequency domain, they have to behave in this way. So any number shifted in this case is going to be looking in the same way. So we continue by just if you want, you can verify, for example, by using the other methods. But yeah, so that was a time shift method. But also you can verify and see whether it is corresponding the value. And here we can also scaling the z domain. So how do we scale the z domain? Number 3, scaling z domain. So if we have, for example, the value, you remember, we are all of our equations are going to be to base on this formula. Remember, z transform, and here is going to be the general format if you want to convert the discrete times domain to their corresponding frequency domain. This equation is going to be true everywhere. So if, for example, you have z of 0 power n somewhere, and then you have x of n on this side, and you want to convert it into their corresponding z transform. This is a discrete variable. You want to, using z transform, you are going to obtain the x, big X, of z over z0. So x of z minus z in this case. So it is very common that if in any case one is a reflection of the image of the other, so it can be a superimposed of the system. So if you want also, you can verify it and just get the information, and you can get the answer, for example. So this is very useful once you are calculating the signal that are superimposed and you want to get the value. For example, if you have U, big U of Z, which is equal to summation of n 0 to infinity of U of n. Remember, we are using this as a Z transform. This is a general form. So you can get its equivalent, which is equal to B Z over Z minus 1. Taking the value of the whole of the system. This one also can be divided into the partial fraction method. I mean, power series or partial fraction. You can put it Z dividing by Z both sides, then you can get that one. So continuing from there, you can have, if it is a U, if it is U of negative n, you can easily get the inverse. So it's going to be 1 over Z over 1 over Z minus 1, which is going to be, you put this 1 over Z, then into, it's going to be into Z minus 1 minus Z, so that side. And this is, in general case, this is very simple calculation, but this brings us to some different numbers that is showing the inverse of n, which is equal to, when transferred by using Z transform, is going to be 1 over the other value that we obtained from the beginning. And this side, the region of convergence is going to be at modulus Z, which is equal to, which will be less. When they say less than, it's going to be from the external Z transform. So the external unit circle is going to be less than internal or external unit circle, so it will depend. So this is very important to know all this time scaling. This is a time reversal from Z time scaling. So you can have different numbers. So we have seen time scale, scaling on the Z domain property. We can also discuss about the differentiation method to find. So we have seen the linearity, the scaling, the time shift, the scaling Z domain, the reversal method. Now we are going to discuss the differentiation. Differentiation in Z transform. So we are going to see the differentiation method. So suppose if you have n(x) of n in this case, so using Z transform, so you can end up getting d big X of Z over dz. So this is differentiation method, and this is, and as we know, this is also true. Remember, having this value of n into negative infinity to infinity of x of n z per n is this one true, then you can say, for example, differentiating all the both sides. Differentiating both sides, you can get the z, the x of z, which over the z, because summation, I mean, from infinity n to infinity of the other value of ours is going to be multiplying nx of n into z minus n, but also minus 1. So we are trying to, so now we are going to multiply z both sides to get rid of z, I mean to get the pure z. So it's going to be the whole side multiplied by z, which is going to be, I mean, it's going to be negative z, or the x of z over the x, this is dx of, which is going to be summation of n is equal to infinity, negative infinity of the other value. We remove negative, it's going to be nx nxn z power n, that is going to be the value of x. So you call it, for example, any coefficient times nx of n. So this is, so the value is going to combine at this side, and so you can remove all these values. So this stands for any coefficient, and this thing can be a number. And then we conclude by saying that n x of n in this side, when using z transform, you are going to obtain any coefficient which can be of this one. Okay, we can call it any value here. Okay, it's let us put like 3 of any value. And then we can have big X of the Z of Z, of course. So this is true once you are given this one. So this is a differentiation method that you can obtain. Suppose if you are given a number including all these values, then you end up getting the differentiation method, which is a differentiation value. So here the properties are given in the table. You will receive them from my notes. You get them using my contacts, which I gave you. Remember to just go there and see and read, or even by seeing this YouTube, you have to go and subscribe and like, even share, to see all those videos every time when I upload. So this is also important. So that was the way how we can get this. These were the properties. We discussed the inverse and their properties. The method is how we can get inverse transform. and then the ways how you can get inverse Z transform or Z transform, and also we are also discussing about the properties, including the linearity, time scaling, reversal, and so on and so forth, as you have seen. So this is one of the important portion for the inverse Z transform. So we are going to see the inverse response. And remember, when we are discussing inverse responses, here we are talking of the system. I mean the systems. For example, in this case, we provide input to the system, then we respect the response. So we are trying to see, suppose if we have two signals coming into the system, how is it going to, how is the response or the outcome or the output going to look like? So we want to see how this can look like and having the system. So suppose if we have an input of xn, so suppose you have input value of xn. So first of all, let me write the subheading of this and see. Okay, let us continue in this way. So suppose if you have an input x, x of n, this is an input. Remember, this one is in a discrete format or discrete time system. To be excited to the system, and we have also y of n in the end to be the system response. So this is a response and this is input. So this also can be called response, time response, okay, or the outcome. So, and also you have a transformation called T. T is going to be transformation. So you remember, you can transform using the convolution sum, the time response, or anything, and which is related to what we are discussing now. And you want to get the output there. So you have T, which is a transformation between x of n, which is input, and y of n, which is a response. Then the system will look like this. So this is a system which is transformation system, and this is going to be x of n in this side, which is input, and the other one is going to be y of n at the end, which is going to be the output. So the response system is going to be y of n, which is multiplied by t, of course, of x of n in this case. So the response system is going to be this. So suppose if you are given any value between, if input value is given and the other one, remember to multiply this transformation to get your response. So it's very important to that this is what we call the impulse response, and the output is going to be impulse response that is looking like in this way. It can be equal to t times its corresponding impulse of n, or unit impulse. So in this case, some of the time, in the other case, it's called the unit impulse. So this is very important. We can also have the response system here, and remember that this system is going to be time invariant, and it's going to be a very, very important once so suppose now you have a response, okay, time response of this impulse response, for example, call it number A, for example, you say impulse response. That is, for example, h of n, that is impulse response, which is equal to, you remember, we multiplied by transformation t of this, for example, the impulse unit impulse, for example, in this case. And you want, for example, you want to get using the system, which is time invariant system. You end up, for example, getting the linear time invariant system can be shown in this way. So it's going to be a linear time invariant system having your response system, which is h of n is equal to t of impulse response of n in this way. So this is so common, and here we are providing input as a unit step impulse. This is also the unit step impulse of n in this case. So it will look the same way. So if they say, if you are designing a system, you need all these impulse, you need all the linear time invariant. We said the linear time invariants are those ones that have various variables, independent variables that can be that can have different signals at different levels, and therefore it's very good to understand. Suppose if you have multiple signals, and to know how to deal them with them, so you come up with a very exciting responses in the end. So this is a general system that looks like it. But suppose if you have to get a response for any arbitrary values, so how will it look like? For example, if you have shifting theorem or shifting values from the system, how are you going to deal with them? So in this case, so if you have an input expressed in this way, for example, having x of n as an input, you can end up having these, having a shift k beginning from infinity to infinity of x of k, for example, in this case, having shifted from any time impulse, unit step impulse shifted from any k value that looks like this. So if this, so you are given in discrete form, the value in the discrete form, and you want your value to look like a time arbitrary responses of response y, for example. So the response y system is going to be, you multiply the other t function, which is t of x of n in this case, which will look like, for example, the normal case that we have seen, is going to be summation of k ranging from -infinity to infinity of x of k, of course, multiplied by the transformation between these values, for example, x of n minus k, like this. So this is t in between, which is a transformation that we say. So this is a shift theorem that you can see. So this is the resultant of the system. So it can be written improperly. For example, we say it's going to be summation from k ranging from -infinity then to infinity this side of x of K. This is the strict theorem, which is going to be of n minus k to this side. So you can multiply them if you want to combine them, you can do like this. But this one remains in the middle as a transformation of your. So this is arbitrary value, or if you have any shifting values, arbitrary that you have never thought of, that they are incoming inputs. So using the system as time invariant, we can obtain, for example, shift theorem from all those sides. For example, you can have h, that is the response of n minus k in this side, having t transformation of unit step of k like this, and which is also our y, which is a time response that we wrote in this way. This is generalization of k, which is negative infinity to infinity of x of k, in this case, putting the impulse response of n minus k in this case. So this is very true, and this is a time response using impulse response. So that is number one. Number two, we say, remember, we are talking about the way how the impulse response and convolution sum can be demonstrated by having different input value. So in this case, we have seen how the impulse response can be taken using shifted or arbitrary values, or when you don't have the arbitrary values. So now we are going to talk about the convolution sum. You will not get surprised when you get all these stars that look like multiplication, but they mean convolution. So any value, for example, x of n convolution, they will look like this star. It will look like a star of y, for example, in a response. So this is a convolution. So there is what we call convolution sum. What does it mean to have a convolution sum? It is an operation that is going to unite together the signals from different sources and just coming together as a single signal. So, for example, here, if you have a response, impulse response, having the response value that is having a convolution sum, a convolution of impulse response. It's the same as saying summation of the other value that we showed, for example, nk shifting, starting from negative infinity to x of k, remember, of h into n minus k. Right. So this is also true if you want to have a convolution sum. So remember, this is what is a convolution sum, and it is an operation that is going to show the values. So if you have, for example, the input, as you said, the linear time invariant system, having the input here, a linear time invariant system, in this case, is going to have its response system here, but also having some other signals here below, as we say, y of n as a response is going to be x of n convolution sum of this linear response in this sum. And of course, the input can be in unit step impulse, or it can be the discrete value signals that can be mentioned like this. So this is very, very important to note any operation that is done by using the linear time invariant system, having the different signals that you can easily determine their output of their systems. So if you want to get the output of the system, which is y, this is going to be a response of the output, then you can easily determine those values. So there are examples. In this case, the examples